Okay, hello everyone. I was just getting things ready here. I had a few more things to get ready than usual since we're going over the exam. I had to get that loaded up. So, reminder that the exam is on Thursday. So that's Tuesday, Wednesday, Thursday, 3 days from now. So 3 days from now at either basically at exam time, at normal class time, 10:20. We're going to start 10 minutes early and then 10 minutes late. So you've got time to download things, upload things, etc. Or you'll have it 12 hours later at 10:20 p.m. The requests for the exams, I haven't put them into Canvas yet because we've got, at last count, 43 people that didn't reply to the Google form. So I just sent an email to those people from our admin email address that says something like the topic is like in big capital letters like final exam time. So hopefully they'll get that taken care of soon, and then probably Tuesday night, early Wednesday morning, I'll get people assigned to the exam. And we're going to be creating new sections like we did last time. So keep an eye out for I believe you'll get an email for the section invite. Now, since you're at home, remember you've got open book and notes for everything that we have given you, all of your PDFs, etc. The cheat sheet, making a cheat sheet or a note sheet, is going to be useful still to get those most important things all in one place. And also writing this by hand rather than typing it. Study after study shows this makes better long-term memory connections, and you'll find that you need it less. No external websites or tools, and the engineering learner code does apply. So we've told you what you're allowed to use is anything we've given you. Now, figure out what is the best way to work on the exam. Do you want to write on a tablet? Do you want to make notes on a sheet of paper? Get whatever you think is the best way for you to do it, and have things handy. Have paper and pencils plural on hand in case anything else doesn't work. You can still do that while you're trying to solve the problems. In the exam, it's going to be similar to the midterm. We're going to have the 24 multiple choice questions on Canvas quizzes, and you'll get all of the questions delivered to you on the Canvas quiz. The writtens you'll submit on Gradescope like last time, and the Canvas quiz ends on time. It is supposed to auto-submit if you don't hit submit, but I would rather hit submit a minute early than have it not get auto-saved for me. So make sure you submit that, but don't submit the quiz until you're done with the written, because you can't see the question once you submit. Now, if you're a few minutes late on the Gradescope submission, that's okay. We're not gonna honor counsel someone who submitted 5 minutes late, because we want to leave it open. We've got to leave the morning one open until the evening people. So just get it done at least, either if it's not by the time limit, soon after. Also, be careful on what file you upload. We had one person for the midterm upload the wrong file. It wasn't even CPP file. It was like a Mac bookmark or something. So make sure you don't do that. We've got the 2 practice exams posted on Canvas, and we're going to go over the written problems from one of those today. You've got all the lecture slides and all your prep work that you've done for the labs, etc. Now, the exam is going to be cumulative. Yes, there's only one correct. The exam is cumulative. It's going to focus on things that we haven't tested you on yet. Now, that being said, it still depends on earlier things. So while we won't say, write the recurrence relationship for this, we would still expect you to know what the complexity of things that we've done since the midterm is. So there's still going to be complexity, but it'll be focusing on things since the midterm. We'll expect you to be able to use things that you use commonly, like vector. We might give you your data inside of a vector and expect you to put your memo for a DP problem in a vector. So just be cognizant of the fact that we aren't going to test directly on things from before the midterm, but there are going to be a few things that we use all the time that we're going to be counting on you to know. You should know basic things like, oh, if I chose to sort this first, that would be n log n. Not too hard. So the things that we're going to be mostly testing on is trees, general trees, binary search trees, AVL trees, hashing and collision resolution, the graphs and graph algorithms, algorithm families, dynamic programming, knapsack problem, things like that. The shortest paths algorithm, but not Floyd-Warshall, the strings and sequences, and not computational geometry. That one tends to make really, really hard exam questions. So the computational geometry is not on the final. Even though it was covered recently, we didn't have it as part of any lab, etc. Okay, there's slides there. Let's skip to the end with let's see, one or two things at the end. So if you decide, this is important for like dynamic programming. Now, I should have, oh gosh, I forgot again. I forgot to update this slide for GradeScope submissions. So if you decide you need a helper function, write it above because you want it to compile. So if you decide you want a helper function, you're going to code it in a file, put the helper above the main function so that the main function can call the helper. If you need a structure, you can write it inside of a function, above a function, not on the right. Sorry about that. I should have updated this slide better for COVID and GradeScope submissions. And the same rules apply from the midterm as what counts as a line. Curly braces don't count as a line. If you make a helper function, the declaration of the helper function does count as a line, but we will make the line count reasonable based on doing either a top-down or a bottom-up solution. Okay, now I'm going to switch over to my editable PDF program here, and it's going to do something wrong. No, I don't want the new version. Okay, I had this open to begin with. All right, now let me see how this looks. All right, one thing that's on here on the practice exam that's a typo, this should say 10:20 to 12:40. I made the practice exam and then asked Professor Darden to change the time by 20 minutes, just to make it a little bit easier on us, but he missed that when he made the Google form. So I said, okay, let's go with the Google form, but I forgot I had put it in the practice exam. So everything else is right. The practice exam is wrong. It is 10:20, like we said on the Google form. And it will show up when we make the exam visible sometime Wednesday, and it shows your time slot. The time slot will be 10:20 to 12:40, or it could be 1:40 if you have extended time. Okay, so what we're going to do is skip through this. Is there a, aha. We want to go near the end, and we're going to work on one of the DP problems. So I wanted to go through some of the written problems here. And I'm sorry about the watermark word practice across the middle. I don't remember if we mentioned that at the midterm. We put that on there because even when exams said practice up here in the top line, we would still get every semester, we'd get someone over at Duderstat or somewhere in another department say, we'd get an email. And the title of the email says in big capital O's, your exam leaked. And I'm like, oh my God, we're ruined. And then I look at it at the picture that they sent us, and it's, oh, that's the practice exam. So to save stress on my heart, I added the big watermark across the middle. I didn't think to take that out for COVID days. Oh, I thought Professor Garden was around answering things like that. Yes. Only one correct. And let's text him and get him on board. Okay. All right, so we're going to work on the written problems from Practice Exam 1 together. And I believe my staff put these also on Gradescope so you can play with submissions there. Now, first thing to look at for the written questions. So I can tell you, we always have a dynamic programming question. Look for the word dynamic programming. So it's important to notice that because it tells you part about, something about how you're going to structure your answer. So look at for the problem that says dynamic programming so you know which one is going to be solved that way. Now, the two things that are really important to solving a DP problem is figuring out what the memo and the basic structure of the code is going to look like, and figuring out what is the relationship among elements within your memo. Now, let's look at the statement of the problem here. It says, we're given a 2 by n board where n is greater than 0. Okay, so we're given a 2 by n board, and given that, we've got, so it's always size 2, and it's got n columns. I always think of it as rows, columns. Okay, so 2 rows, n columns, and we're going to tile something, and then if we look down at the requirement says your solution must be O of n time, and you can use up to O of n auxiliary space. So that tells me a little bit about what my memo is going to look like. The O of n space tells me, I'm probably going to have something like O of n memory because I need to have that amount of space in my memo. So I'm going to have about n elements in my memo. And I'm probably going to have a loop or maybe 2 loops. I know that I'm not going to have like nested loops because that would probably be more like n squared. Although we have to be careful on the Deals on Meals Lab 10 question. That one does have a 2-dimensional vector and it has nested loops. It's just that one of the dimensions is always size 6. Here, even though the tile thing that we're supposed to produce has 2 rows, we only need 1 element for every column. Okay, so now let's look at the problem. It says we're given 3 types of blocks, and we're gonna tile this board, whatever a board means. Could be a game board, could be a cutting board, could be like the backsplash on my wall. So I've got 3 types of tiles to use, and I can tell them apart when I put them up. I can tell how things were made because, oh, maybe the vertical ones might be like some of them are gray, some of them are white, and the horizontal ones, some are gray, some are white. Or maybe the vertical ones are gray, the horizontal ones are blue, and the square ones are white. So I can tell them apart. And we're looking for the number of distinct ways to tile this board given the dimensions. And we've shown you the 2 by 1 and 2 by 2 and 1 by 2 pieces in solution. So if I said how many ways is there to tile something of size 1? Oh, well, there's only one way to do that. I've just got to grab one of those. So if n is equal to 1, that's the only thing I can do. If n is equal to 2, there are 3 ways that I can do it. I can use one of the square blocks. So I can do the big square block. I can put 2 vertical ones next to each other. or I can stack two horizontal ones on top of each other. All right, so I've got for n equals 1, there's one way. For n equals 2, there's 3 ways. And beyond that, it's going to be a little bit harder. Now, the word distinct, we're going to come back to that in a little bit. That's going to change one thing in our solution. And in terms of points, it changed like 1 or 2 points in the problem if you didn't get the distinct part right. So let's work on the basic pieces of a solution to this problem. Okay, so I'm going to have a vector. Of, let's see, everything here is integers. Let's stick with integers for the vector. I'm given an integer. I want to return integers. Since I want to return an integer, let's make it a vector of integers. Okay, so I've got a vector of integers. We could call it memo, for instance. And I'm going to give it its size up front. I'm going to make it size n plus 1. Now this makes it easy for me to do zero-based indexing. Now, I'm going to do this slightly differently from the solution that's coded. It turns out they're equivalent. Okay, so let's say I want to start out with my memo sub 0. I could say memo sub 0 is equal to 1. There is one way to tile a board of size 0. Don't do anything. But that is still one way to do it. Now, I could do memo sub 1. There's one way to tile a board of size 1, which is to use one of the vertical pieces. Now, we did the base case for n equals 2. We could put that in there, and that's what the solution that auto reveals at noon has got in there. But let's go with this basic one, and then we'll see how it builds up from here. Okay, so now I've got to run a for loop. For, and then we can use an int here. We could use a size t. I would simply make it consistent with what we're given. So let's say int, since n is an integer, for int I is equal to 2, because I've got to do everything from size 2 on up. I is less than or equal to n, because I need to tile the board up to the last position, and we're going to plus I along the way. Okay, so now we got to figure out, we got our basic format of our solution. Now what we need is to figure out how this new element of the memo sub I, how is it related to other things in the element? Or sorry, other elements of the memo. Okay, so how is it related to other elements of the memo? Well, let's go up from size 1 to size 2. So how do I get size 2? So if I start with, if I'm trying to solve size 2, I could go back to size 0 and add all 3 of these. So when I'm trying to work on memo 2, I could say, hey, let's go back to size 0 and add 3 and add, basically that produces 3 more. And that's actually going to be a multiplication, because whatever I started out with, I could do it this many more ways. Also, I could go back to size 1. So I could go from, so when I'm trying to do n equals 2, I could say, hey, go back to n equals 0, and whatever I had there, multiply it by 3, because I could either add 2 vertical ones, I could add 2 horizontal ones, or I could add a big square one, and we're not going to add 3, we're going to multiply by 3. Because whatever I had I had some number of ways to do it. I've got lots more ways to do that because for every one of those other ways, I could do one of these. I could also go back to n equals 1. N equals 1 looked like that, and what I could do is I could add one more, vertical one. But wait a minute, I've got a problem here. Because when n was equal to 0, there was one way to do it. 1 times 3 is 3, plus one more. So that's 3 plus one more is equal to 4, and we know that's wrong. We said there are only 3 ways to tile size 2. And this is where the distinct comes in. Because I can't tell this one apart from this one. It's got 2 vertical ones next to each other. I can't tell them apart because I can't tell, oh, I put one down and then I put another down in a separate size, or I just put 2 down to make that size. So what we've got to do is we can't multiply by 3. We've got to multiply by 2 because we're not going to double count. So no matter what I've got, I can always add one more to that number of ways. But really, it's not a plus 1. This is going to be a multiply that previous thing times 1. All right, so my memo sub I is equal to memo sub I minus 2 times 2 plus memo sub I minus 1. Now, that's our relationship, and that's critical to getting this right. If, like we said, you forgot the distinct and left the times 3 in there, you'd lose like 1 or 2 points. Not that huge a deal, but if you wanted to get all the points, you've got to notice how to get rid of the extras in there. And that's basically it. That's the end of the for loop. And then I can just say, hey, let's return memo. I can say either memo sub n, or I could say memo.back. Either one of those. And that's the end of this problem. Okay, now usually we have, when we go over this one, we usually have a bunch of questions about getting the counting. So yeah, it's basically we go backwards 2 and multiply by 2, and we add going backwards by 1, and really, oh wait. Now there could be a times 1 on the last one. Doesn't really need to be there, but that's how we got there. I forgot my semicolon. So we go back by 2 and multiply by 2 for every one of those, and we go back by 1 and we add it in. And now we can see that now we get the memo sub 2 correct. We do get 3 for memo sub 2, and then it goes up from there. Now when we gave this problem, a couple of years ago, I don't remember how long, 4 years, 3-4 years ago, we while we were grading it, one of my staff members said, hey, I think there might be a closed form solution for this. So he went up to the room we were grading in, he went up to the whiteboard, derived this really complex closed form solution that didn't need DP, and it had like this one strange term if n was odd and a different term if n was even. And we actually had one person who took the exam, came up with a closed form solution, and was even cleaner than my staff members because he got the integer division to come out right, so he didn't need special cases for any even or odd. So I'm not going to say that whatever we give you is going to have a closed form solution. Usually they do not. But if you do come up with one, that's great, but make sure it's right. Make sure it works. because if you put all your eggs in one basket, you can lose a lot of points. If you try to make a closed form solution, you don't get any points for having a memo of the right size. You don't have points for the relationship between elements of the memo. You might lose a lot of points if you try a closed form solution that doesn't exist. So the DP solution will always exist. It will always meet your time and memory constraints. Okay, any questions left on this one? Hopefully we'll get, Professor Darden can take care of those. Okay, so now this exam was a little bit odd in that it had 2 other questions. So normally we do just 2 written questions. This one had 3 of them, although the second and third ones were related. Okay, so let's go through here. All right, so we've got a question here which says we've got a set, so we're trying to make a set, and we want to be able to efficiently see if it contains a given element, and we've got a following definition for a binary tree node, and it says we want an average case, so we got to implement exists, it's got to have average case log n, and we may use up to log n auxiliary space. Okay, so we're given a binary tree. So we don't need to create the binary tree, we need to create the exists function. So the nodes don't count against our memory. The reason for the log n is if someone came up with a recursive solution that was not tail recursive, we still wanted to give them the room to do that. And so it says, in the average case. In the average case, you must do this. So it could be, if it was a worst case, you might break these constraints. It might be O of n time in the worst case. But in the average case, we proved why the average tree is branchy rather than stick-like. So in the average case, we should be able to get this in log n time. And all the solutions that we wrote in our answer PDF are O of 1 auxiliary space because they're either iterative or they're tail recursive. So we can implement this one either way, and the solution, I know the solution gives you both the iterative and the recursive ones. So let's do an iterative solution here. Because we get maybe a little less practice with that in general, let's do a recursive solution to this. Okay, so we've got to implement exists. All right, so if I'm going to do recursive, I've got to have a base case. So let's do that first. If node equals null pointer. Now, equivalently, we could say if not node is faster to type, is certainly faster to write. On a handwritten exam, I'd really get used to the not node here. But since we've got since you're typing, it's not too bad either way. So if that's the case, then I'm going to return a null pointer. So if I've tried looking left, right, left, etc., and I don't find it, I say null pointer to say it doesn't exist. Oh wait, whoops, I goofed. We're supposed to return a Boolean. Okay, so we're supposed to return a Boolean, so that's going to be false. Even simpler. Okay, so if I've reached a null pointer, I know that what I'm looking for is not in there, so I've got to return false. And then I can do a bunch of ifs because I don't really need an else if because I'm doing return statements. So I can just say, all right, so if this node, what is inside of it? The value inside of it. So if this node's value is equal to the value I'm looking for, then I must have found it, and I can return true. Okay, if I didn't find it, then I've got to figure out whether I should go right or left. So if I'm going to do a comparison here, and I like to do the left subtree first. I try drawing the arrow your way. I try to do the left subtree first. And I also try to use less than if I can on my comparisons, because that's what the STL would do. Now, since it's an integer, it doesn't really matter, but I like to do these things. So if I'm going to say, if the value I'm looking for is less than what I find in this node, then I'm going to make a recursive call. I'm going to return, I'm going to return whatever's in my recursive call in node left, comma, val, because I've always got to give it the value. Okay, so if it was less than, I'm going to return what's in the left subtree, else I'm going to return what's in the right subtree, okay, so I'll either return what's in the left subtree or what's in the right subtree, and that's about it. Pretty simple function. So really just testing, do you know how to do your binary search tree? And since we've got recursive calls that are tail recursive, we don't need any stack space. And then as we make the recursive calls, we get down to one of these two base cases. We really have two base cases. We either get down to the point where we don't find anything and we return a null pointer and it just goes all the way up the stack right back to the original caller in one step, or it returns a true. From finding it, it goes all the way straight back to the original caller of exists. Okay, so that's the recursive version. If we write an iterative version, we would basically just do a while loop. While node is not null pointer, and I could modify node because it's a pointer passed by value. So if I modify node, I'm not modifying somebody else's original like head pointer to their or root pointer to their binary tree. So I could just do like a while loop while node is not a null pointer. If it's equal, return true. If it's less than, move left. If else, move right. And I can just set node equals node left or node equals node right and walk through it with a while loop. And if the while loop ever exits, because we found null pointer, that's when we'd have to return false. Okay, so not too hard to do for that one. Next problem says a set, blah, blah, blah. Oh, it looks like we're going to do it with a hash table. Okay, so we're going to do it with a hash table, and we've got something. I tried to make this when I originally wrote this question. I haven't modified it. When I originally wrote this question, I wrote exists kind of like the 26. I wrote it as a standalone function. This is not a member function. Let me see. I'm not sure if that's getting on there. Okay. I had to look back at my live feed rather than my delayed feed to make sure you can see that. Okay, so this is not a member function. So we're going to pass in the entire hash table, and I thought this would be easier than making it a member function, because then I'd have to tell you the name of the member variables instead of just putting them in the parameter list. But it actually, I think, made it a little bit more confusing. So when you write the solution to this one, you can't just say like bucket sub I. You've got to say tbl dot bucket sub I. So we've got to be careful with our with the fact that it's not a member function. We've got to actually look at things directly. Okay, so it says then, so we got a hash table problem. Suppose this hash table implements quadratic probing. When hashing, the hash function is simply value modulo m, so we don't need a hash function. We just take the value modulo the size of the hash table. Well, the size of the hash table. Don't write it in terms of m. There is no m here. M, the size of the hash table, would be tbl.buckets.size. Okay, so m doesn't exist. That was another problem that a lot of students made. That was a minor one, though, is forgetting that m didn't exist and just using it instead of tbl bucket size. And it says implement the exists function for a set based on a hash table. And it says your solution must implement quadratic probing. If you don't do quadratic probing, then you lose a lot of points because, hey, you already know how to do linear probing. You did it for the lab. This is kind of like the lab, except A, it's quadratic probing, and B, we made it a standalone function rather than a member function. Okay, now there's a bunch of ways to write this. I'm going to go through the way that I thought of it myself. The one thing we've got to make sure of is that we've got to make sure we don't loop forever. And you might have found this on Lab 10, the last test case. I forget what the name of it is, but the last column that's listed is basically, and there's a hint for it if you TLE that test. It gives you a hint saying you've got to be careful. Like, what if everything was deleted? You've got to make sure you don't loop forever. So I think I might write this one differently from the way the solution's written. I'll write it a way that I think students thought of more. So the important thing is we've got to make sure we don't loop forever. And so we're going to look for something. We can stop if we ever find an empty bucket. We can say false. Nope, it's not in there. And if we ever find a bucket that is filled and has the value we're looking for, or should I say occupied, and has the value we're looking for, we can stop. Okay, so I'm going to have to make a few variables before we start looping. So I'm going to have to know where to start. And I think we can get away with mostly just like I say. So I need an index for where it's going to be. Okay, so let's say just size t. My starting index is equal to that value modulo tbl.buckets.size. Okay, so that's my starting index. And then we could use another variable for my current index, or we can compute it. Let's just make another variable. Yeah, we'll just leave it at that because we're going to have to initialize it inside the loop. Okay, so now I'm going to run a for loop. Okay, so I'm going to run a for loop through these, and I'm using this to make sure I don't loop forever. Like if everything was deleted or somebody overfilled it and I got residual squares or whatever happened, I want to make sure I don't loop forever. So that's what this for loop is going to do. And remember what we've got to do. We've got to check the original location, and if that does not give us a match, we've got to go at that index plus j squared for j equals 1, 2, 3, etc. Okay, so curly brace here. So my index is going to be equal to my start plus j times j. So when I start out at j equals 0, that is my starting location. Oh, except I've got a problem here. I'm already writing bugs. That modulo tbl.buckets.size. So I can't forget to do the modulo, because if I do that, I might go off the end as j gets larger. Okay, so now I can start checking what's in this bucket. So each bucket has a vector of, it's got a vector of buckets of integers, and it's got a vector of statuses. Okay, so I've got my vector of buckets, my vector of statuses. We'll assume those are the same size, because that would be bad if it wasn't. Okay, so what I want to check is I want to look for either I found it or I'm done. And we can do this in any order. We can check for an empty one first, or we can check for an occupied one that the value matches. Order doesn't really matter here. Let's look for what we want. I want to find a match. So if this one has, and I'm going to need two conditions here. So I'm going to space this out and do it like I like to format it. So if tbl dot, let's do status first. Okay, so if that's equal to status colon occupied, and tbl.buckets subindex is equal val. If that's all true, I can return true. Okay, if that's not the case, so we didn't find it, then we've got to see if we found an empty one, we want to stop. So this one would just be, I just need the status. I need to see if table dot status subindex is equal status colon empty. So if I find an empty one, I can immediately return false because I reached the end of the cluster. And if that's not the case, we've got to go back through the loop. Now, if we ever get out of this loop, we've got to return false. Because we searched all n buckets. Or at least I searched n times. So I either searched all n of them or I wrapped around or something. But I've got to make sure we don't loop forever. And that's the end of the function. So this one's actually written differently from the way I originally wrote it. I originally wrote this as a do while loop because I knew I had to check at least one bucket. So I wrote it as a do while loop and then updated my index. But we can write it as a for loop also. Just either way we do it, we've got to make sure that we don't loop forever. Okay, so that's the second written problem. Okay, now let's see, I'll check back on the, okay, looks like, okay, so you've been taking care of those. Cool. All right, so I think we're good on those. And then that's just, yep, that's the end of the exam there. Okay, and then the excuse me, the PDF has solutions to these, although you have to type them in from there. Just make sure you don't copy from the PDF, because copying code doesn't work very well, because PDFs have these little hidden characters to make the line spacing look pretty. Okay, so let's go back to slides. Let's make sure that that updated correctly. Okay, so we're going to go back near the beginning. Okay, we're on trees. Aha. Okay, so this is slightly out of order. I just realized I did the trees before hashing, but that's sort of logically the way I would think about it. We did the hash tables first because we really needed them for project 3. Okay, so we talked about general trees where we could have any number of children of a node, binary trees where we have 2 children at most per node, binary search trees where we have a rule about where things go, left or right, less than or greater than, equal can go either direction. We just have to make a decision and be consistent with it. And then AVL trees, which are self-balancing. Now, when we make a decision about duplicate values, I think we said duplicate values go left. It doesn't really matter for a couple reasons. One is that if it's in there, we'll find it. 2 is that if we're doing AVL trees, where we decide to put it might not be where it stays. So I could say, hey, I've got a tree, let's insert 5. Let's insert another 5. Well, duplicates go to the left. Let's insert another 5. Duplicates go to the left. But then I've got to do a rotate right at the original 5, that one, and then I end up with 5, 5, 5, and now there's duplicates on the left and on the right. It doesn't matter, because if we try to do a search for 5, we will find the one closest to the root first. So although we make a rule about where we put them just so that we can have a way to write the code, where they end up might be different in an AVL because of rebalancing. Now, we've got a problem here that you can work on for a few minutes. I'll let you start out on this, and then I've got a blank slide in here. What we'll do is we'll do a couple of these inserts together after you've had a few minutes to practice them on your own. So take a few minutes, do a few inserts. As soon as you notice a point where a rebalance is needed, do it, and then we'll do some together. Okay, actually, while you were doing that, I updated one of the practice exams with the right start and end time. I'm going to re-upload those. Okay, so let's see. We've got 4, 2, 3, 5, 7. Okay, 4, 2, 3, 5, 7. Let's just write that down. 4, 2, 3, 5, 7. Okay. All right, so we start out inserting. So we start out 4 becomes the root. We add 2 is less than 4, so 2 goes over here. 3 is less than 4 but greater than 2, so 3 goes here, and we're out of balance. If we look at our balance factors, so I've got a balance factor of plus 2 with a minus 1 to the left of it, which means we need a double rotation. So I like to write things down. I need to do a double rotation so I don't forget. I want to do a rotate right at 4, but before I can do that, I've got to do a rotate left at 2. Okay, so rotate left at 2 goes first, so we get 4, 3, 2. Okay, and then we can do the rotate right at 4, which gives us 3, 2, 4. Okay, so we've taken care of that. All right, so what if we change colors? What if we insert something else into the tree? All right, so if we insert a 5, it would go to the right of 3, to the right of 4, and we're still in balance. If we check all the balance factors, it still looks fine. All right, if I add a 7, well, 7 goes right of 3, right of 4, right of 5, 7 ends up down here, and now if we look from the point of the insertion upward, 7 is fine, it's a new node. 5 has a balance factor of -1. 4 has a balance factor of -2. 4 needs to be rebalanced, and it has a negative with a negative to the right of it. I'm drawing it my way rather than your way. It has a -2 with a -1 to the right of it, which means we only need a single rotation to fix this. So let's just draw it up here. So I've got to do a rotate left at 4, and get used to this notation for the rotations because we use it on the exam. Okay, so we say rotate left at 4 gives us then 3, 2, 5, 4, 7. Okay, so that's the point that we're at now. And let's do, so we took care of those. Let's do 1 or 2 more. It was, after that was 8, 9. And there's probably, by the time we do at least one more of these, we'll need another rotation. Okay, so let's change colors again. All right, so I've got to insert 8. So 8's got to go right of 3, right of 5, right of 7. 8 goes here. Now let's check our balance factors. 8 is fine. 7 is 0 minus 1 is -1. 5 is 1 minus 2 is -1. 3 is a balance factor of 1 minus 3 is -2. So 3 is unbalanced. It's a negative with a negative to the right of it, which means we only need a single rotation. So I've got to do a rotate left at vertex 3. And this is a good one because we've got to keep track of what happens to the child that moves. So 5 moves up, 3 moves down, 2 goes with 3, 7 and 8 just stick right to 5, and then 4. So 4 used to be 5's left child. 5 got a new left child. Therefore, 4 had to go somewhere. Well, 3 lost its right child. 3 has room for a new right child if it needs one. So 3 gets 4 as a right child. Now, when there are no duplicates in the tree, it's easy to figure that out. There's only one place that 4 can go and still be findable in a binary search tree. It must be to the right of 3. But if there are duplicate values, you've got to keep track of who lost a child, who gained a child. The one that lost a child is the one that can gain a child. The one that gained a child is the one losing a child. So when 3 and 5 change roles, 5 goes from being a child to being a parent, and 3 goes from being a parent to being a child. 3 loses its child, 5 gains a new child. Therefore, if 5 has a left sibling to give up in the case of a left rotation, 5 has a left sibling to give up, which means 3's right sibling can become what was 5's left. Okay, so we took care of 8, and then we can move along and do 9. If we add 9 in here, we get unbalanced. We've got to do a rotate left at 7, which then gives us 5, 3, 2, 4, 8, 7, and 9. We got a perfectly balanced tree, kind of crunched at the bottom there, but we got a perfectly balanced tree. We can do at least 2 more inserts before we have to rebalance, because everybody has a balance factor of 0. One insertion can only make someone unbalanced by 1. It would take at least 2 insertions before we have to do any more rebalancing. Okay, hashing. So we already did the programming problem for the binary search tree exists, hash table exists with quadratic. So just to go over these again, so we have the hash functions. So the hash function, remember, has 2 parts. It's the compression of the translation of the key. Now, when we did the hashing coding problem, the translation of the key, there was no translation step. The key was its own translation, because remember, T, the translation is there to make sure we turn whatever the key is into an integer. And then the compression is to make sure we have a valid index. So the most common, the simplest compression function is just modulo table size. Okay, so we've got hash functions. We talked about hash tables, and when we put things in a hash table, we're going to have to deal with collision resolution somehow. We've got separate chaining, which makes a linked list or some other structure come off of each bucket where everyone that's supposed to be in that bucket is there. And then the other ones, which are collectively referred to as open addressing, because they try to find an open or an empty location in the table in which to store it. Now, one other thing, I don't see it here. One other thing to remember is also we did dynamic hashing. That's what you're doing in Lab 10 when you do the rehash and grow to make the table larger because it has become too full. At some point, we're going to do dynamic hashing. And dynamic hashing can be used with any of the other collision resolution techniques. In Lab 10, you're doing linear probing with rehash and grow. In my code, in the sample code folder on Canvas, I gave you a hash table that never ever grows. And that one uses separate chaining. What would be a good practice, maybe, would be to take that one, make it instead of an array containing the linked lists, make it a vector containing the linked lists, make a rehash and grow, know how many things are in there, like you'd have to know a size, how many things are in the hash table right now, because the size of the hash table doesn't tell you that. You can have a hash table size 10 and 50 things in there. Or you could have a hash table of size 10 and 4 things in there. And then you'd have to resize it when you decide that it's too full. And the real trick would be you never ever make a new node. You only just move nodes from one linked list to another linked list. And that would be a bit trickier because that's what the STL actually does. The STL implements the hash table using separate chaining, and nodes move around between the linked lists. And the reason that it does that is that the STL, the standard unordered map and standard unordered sets, iterators are basically node pointers. And so if a node moves from one linked list to another, if I have an iterator, I say, hey, find me this thing, and the STL gives me an iterator, that iterator is valid as long as I don't tell the hash table to remove that thing. the iterator is always valid because the node just moves between different linked lists and never gets recreated or destroyed until that item gets either removed explicitly or erased or cleared. Okay, so what is the complexity of inserting into a hash table with m slots that stores n unique keys? Now, with linear probing here, the equation for average is a little complex because remember that average hashing with linear probing and quadratic probing is the one that I said in the lecture that we wouldn't give you that we wouldn't expect you to know these formulas. So we can come up with sort of an estimate of the average for linear probing, but really that one's got it. The right answer would be going back to the slides for it. Okay, so I'll just start. You can start thinking about these. I'm going to make headings for these while we do them. Okay, so for separate chaining, best, worst, and average. And then for linear probing, okay. So the best in both of these should be really easy. O of 1. We find it exactly where we expect to find it, or we find a bucket that's never held anything and we know it's not in there. So we can get lucky and either find it on the first try or we find that the place that it should be is empty. Okay, what about worst? Well, then worst would be the same for both of these. Worst could be O of n. In separate chaining, I could have all n items in the same linked list. In linear probing, I could have all n items in one big cluster. And I look at the beginning of the cluster and I probe all the way through all n of them, and then I eventually find it's either the last one I look at or I find an empty location and know it's not in there. Or I could wrap around to the beginning. I could go all the way back to O of m. I could wrap around through a bunch of full, occupied, deleted, wrap around and discover I'm back where I started. So O of n in the worst. What about the average case? Well, with separate chaining, that's the O of alpha, which is equal to O of n divided by m. In the linear probing, this is the one that comes from the slides. That was the big complex 1 over 1 minus 1 over 1 minus alpha or something like that. And our search and insert complexity is going to be the same for these. Whether I'm trying to insert into it or search for it, I get the same complexity. Okay, graphs, that's actually a graph representation of the internet with big data sets shown very brightly. So when we talk about graphs, first of all, we did graphs in general. And we talked about a bunch of different terminology, which we've got a summary on the next slide. And then, so someone said O of 1 plus, so O of 1 plus n over m, which is the same as O of n over m. Okay, so we got a bunch of different terminology on the next page. We've got the adjacency list versus the adjacency matrix, when to use them, depth first search and breadth first search, the MST algorithms that really are working on a graph, and the shortest path, Dijkstra's algorithm. So with the graph terminology, so lots of things that we talked about, edges, vertices, or nodes, we tend to still use those interchangeably, so be ready on the exam to see either vertex or node, vertices or nodes plural. The degree of a node, actually, I don't think we ever defined degree of a node. So degree of a node is just the number of edges. I'll make sure we don't have that on any exam questions. The weight, so when we talked about weighted graphs, weight could be dollars, miles, time, all kinds of different things. It's just basically a number associated with an edge, and it is when we have some sort of constraint that we want to minimize or maximize, that weight, whether I say cost or weight, contains different connotations, but they all mean the same thing. They are the value that we are going to take into account when we try to minimize or maximize. We looked at directed or undirected graphs. We looked at a simple graph, and unless we say otherwise, you can assume that we always mean a simple graph unless it says something different. Simple graphs meaning no self loops. So no node will go back to itself, and we won't have parallel edges between two nodes. Now, if it was a directed graph, we could have different directions. That would not be violating the simple constraint for a directed graph. Now, we talked about sparse and dense and when to use the different representations. So in a sparse graph, we could say the size of E is approximately equal to the size of V, which really means the number of edges is some constant times the number of vertices. Or we could say, like I said there, that it is much less than V squared would be another way of saying it. In the dense graph, the number of edges is proportional to V squared. When we have a sparse graph, we want to use the adjacency list representation. When we have a dense graph, we want to use the adjacency matrix. Now in project 1, we really actually had a graph search, but we didn't have either an adjacency matrix or an adjacency list. We figured it out. We said, oh, well, we can look northeast, southwest, or in whatever order is specified by the Hunt order. And in project 4, we didn't actually, at least in parts A and B, we didn't have an adjacency matrix or list. The graph was dense, but so dense and so big that we couldn't afford the adjacency matrix. We figure it out logically. We say, hey, if you're trying to connect land to sea or sea to land, that's invalid, and the easiest way to invalidate that is to just say the distance is infinity between those two vertices. So we really didn't store it, we calculated it as we needed it. Now in part C, you can afford a distance matrix. It's a completely connected graph, and you can fill in the values in there. Because with the limited n, we actually had room for that adjacency matrix. But in project 1, we weren't even at the point where we had the term adjacency list. Project 1 was very sparse. Every square was connected to at most 4 other locations. And those near the edge or those next to a impassable terrain, a number sign, would be less than that. So we talked about a simple path. So a simple path is a path where we don't repeat any vertices in the path. Then we had a cycle, which is like a simple path, except the beginning and end are the same. So I can start from home, visit a bunch of other different vertices, and return home. We talked about the Hamiltonian cycle, which was the visiting every vertex, not just some of them, and returning to our starting location. We talked about cycle connected graphs in general. We talked about the spanning tree and the MST problem. Now, different graph problems that we talked about. The one you've done the most on is, of course, traveling salesperson problem. Got a cat drinking water, if you can hear that. So the traveling salesperson problem is our most one that we've worked with the most because of Project 4. We also looked at graph coloring. We looked at the knapsack problem. The N queens really is sort of a graph problem, every location in n queens is adjacent to everything on the same vertical or horizontal or diagonal line. It really is a graph problem, and it involves a search tree. Even if we don't have a representation of the search tree, we still do the search. And our search within the bounds of the problem space is what we call the search tree. Now, with this graph, it says do prims and Kruskal's on this graph. Now, if we were doing prims, we would have to say a starting point. Now, I think after doing project for part A, I think you've done enough prims. Let's do this with Kruskal's. Now, if we're doing it with Kruskal's, we don't need to tell you where to start. Kruskal's starts with the lowest cost edge. So if we're doing this with Kruskal's, it's also kind of easy to do Kruskal's without rewriting a sorted version of the edge list. If we're really careful, we can do Kruskal's on this graph just by circling edges we keep and crossing out edges we don't keep. And we're not going to keep any edge that would produce a cycle. So if I look through the graph, I've got one edge of weight 1. It's got to be selected. It's in there. Okay, now we've got two edges of weight 2. And actually, let's keep track of who's reachable. So C is reachable. We're done. F is reachable. Okay, so we've connected those, and this will help us with the cycles a little bit. All right, so now we've got two of edge weight 2. We could choose them in any order. We would, at worst, we would find different MSTs if we pick one and then can't pick the other, or in this case, we'll end up picking both. So I can pick the edge of length 2, which includes D in that graph. I can pick the other edge of length 2, which includes G. And really, I don't have a forest on this one. I'm really growing one tree so far. Okay, edges of weight 3, they don't exist. Edges of weight 4, I see one of them, and it's disconnected, so let's change colors. I can take the edge of weight 4, and then those vertices become connected to each other. Now how about edges of weight 5? Okay, there is a 5. We can take that edge of weight 5, and that'll include E in the graph. And now all of the vertices have been selected, but I don't have enough edges because I don't have a connected graph yet. We've got to keep going. Okay, so we took the edge of length 5. How about the edge of weight 6? Edge of weight 6, ooh, that would produce a cycle, EFG. So we can't take that edge of weight 6. All right, how about the edge of length 7? If I choose the edge of length 7, I would have a big cycle, D to C to F to E and back to D. So I cannot take that edge of length 7. That one's out. All right, what about edge of length 8? Aha, there's two of them, AC, BD. I would tend to check them in alphabetical order. So that would be AC. It doesn't really matter which one you pick. It turns out we're going to be able to pick one of these. So let's say we pick the edge BD. So we pick the edge BD, and now what I'm going to do is I'm going to recolor a little bit to show that they're all part of the same subgraph. So B and A are in now. Oops, I need to change pen color. So B and A are now in the red. I think red is what I'm using, red graph. And now when we look at the other edge of weight 8, we cannot take that. That would produce a cycle. Edge of weight 9, this one produced a cycle, that one produced a cycle. Edge of weight 10 would produce a cycle. And that's everything. Okay, so there's our equivalent MSTs. We're going to pick one of those edges of length 8, but we can't take the other. And that was a greedy algorithm. We picked edges that didn't produce cycles. We never changed our mind. We always made the best choice we could right now by picking the shortest one that didn't make a cycle. So there's Prim's algorithm, and we've gone through and analyzed this extensively. Kruskal's algorithm, we just ran through it. We sort all the edges. We try to insert them as long as they don't produce a cycle. And what did we do for this? It's not on the slide. How did we keep from producing cycles? Union find. So union find could be on the exam because it's part of Kruskal's algorithm. Now, we presented it before the midterm, but we've also gone through it a lot more now. So it could be fair game for an exam question. All right, Dijkstra's algorithm. So Dijkstra's algorithm, also a greedy algorithm for solving shortest path. We're going to assume, if we're using Dijkstra's, there are no negative weights in the graph because they mess up the greedy strategy. Now, we will find the single source shortest path. So whichever one we set at a distance of 0, we will find the paths from that vertex to all other vertices. Okay, and Dijkstra's is much like Prim's. We can use the same basic approach of do we know the shortest path to this vertex? True or false? What is the distance of the shortest cumulative path? And this, when we say shortest path, the word cumulative is implied. With MST, it was always the shortest edge. Now it's the shortest total path length, and P is who's the predecessor to get here. So if we did this one starting at node A, all right, let's run Dijkstra's algorithm starting at node A. Let's run it together. Now, we're going to have to be really careful if we don't make a table, and we don't really have room on this page to make a table. So we got to be careful. All right, so I'm starting at node A. Node A is done because it has a distance of 0. So really what we did was before the loop started, we set A to distance of 0. Then we find the smallest false one. We got a bunch of infinities. If someone doesn't have a weight written next to them at all, we assume it's infinity. So we found the smallest false one, and we mark it as true by circling it. Okay, so now step 3 is update the neighbors. All right, so if I'm going to update the neighbors, I can get to B at a cost of 4 plus 0 is 4. I can get to C at a cost of 8 plus 0 is 8. And that's everyone adjacent to A. Okay, we go back through the outer loop. So I haven't done this V times yet. I've only done it once. So we go back through the outer loop again. Step 1, find the smallest false one. Okay, smallest false one. I've got 4 or 8. I picked the smallest false one. So B is now true. Oh, and I've got to remember I did use that edge because A goes to B. And that would be in the table, the Dijkstra table, I suppose I should say. It would be in Dijkstra's table that would say B's predecessor is A. Okay, so then I check the neighbors of B. Can I find a better way to get to them? Okay, I can get from B to C at a cost of 9 plus 4, 13. Not better than 8. We don't do that. We can do B to D at a cost of 8 plus 4, 12. That's better than infinity, so that's fine. Okay. And really, I should have put like a little arrow here to say, hey, that's the way it would have gone. That's the way that would have gone. We haven't really used them yet. They're not solid. These are just potential choices. I can get from B to E at a cost of 10 plus 4 is 14. If I go that way. Okay. Now we go back through we finished updating the neighbors, go back through the outer loop. Still not done. Step 1, find the smallest false one. Distance of 8, 12, 14, or a couple infinities. So 8, this becomes true. So that's step 2. We can say, yes, I'm definitely going to use that edge. And now we update the neighbors of C. So that's step 3. So update the neighbors of C. So I've got A is already true, B is already true. We never update anybody that's true. I kind of glossed over that before. C to D. I can get to C at a cost of 8. D at a cost of 2 more is 10. Hey, that's better than a cost of 12. So hey, I can get here at a cost of 10 if I go that way. And I'm going to erase the other arrow up here because I'm not going to use that direction. Okay, I can get from C to E, C to F at a cost of 8 plus 1 is 9. That's better than infinity. I would go that way. And that's everywhere that I can update from C. So go back through the outer loop. Step 1, find the smallest false one. I've got a 9, a 10, and a 14. Looks like 9. So 9 gets marked as true. That's step 2. And this, I can solidify that. I'm really using that edge. And now step 3, update the neighbors of F. Well, I can get from F to D at a cost of 9 plus 9. That is not better than 10. I can get from F to E at a cost of 9 plus 5. 14. Since it's not better than 14, I wouldn't update it. I can get from F to G at a cost of 9 plus 2 is 11. That's better than infinity. And I would go that way if I used it. Alrighty, back through the outer loop. Smallest false one. Looks like D at a cost of 10. So D gets marked as true. That's step 2. And I'm really taking this edge. And then we update the neighbors of D. Okay, neighbors of D, lots of true ones. E is false. I can get there at a cost of 10 plus 7. 17, not better than 14, so we don't update it. Everybody else is true. We're done. Okay, go back through the outer loop. We're still not done. Pick the smallest false one. That's G. Step 2, mark G as true. I'm really taking this edge. Update the neighbors of G. I can get from G to E, 11 plus 6 is 17. Not better than 14. Leave it alone. Okay, go back through the outer loop. Step 1, smallest false one. E. Oh, it's the only false one. So E, we really did take this edge. And update the neighbors. There's no neighbors to update. We're done. So we have found all of the paths. Now, in this one, I drew the arrows backwards in this one. Because really, since we started at A, really the arrows should all be going in the opposite direction because we really did do single source shortest path. Okay, algorithm families. I love this comic. Oh, you get it again. Anyway, so we looked at the different algorithm families: brute force, greedy, divide and conquer, dynamic programming, backtracking, branch and bound. Brute force is, I put simple in quotes because sometimes it's not simple. How do you generate all n factorial possible permutations? Turns out that's hard. I mean, that's what GenPerms does. GenPerms is doing all possible permutations. And if promising just said true, it had one line of code, return true, and nothing else, that would be brute force. We would try everything. But in Project 4, we don't just have promising return true, we do branch and bound instead. So brute force is sometimes simple, sometimes not. It tends to do the most inefficient way of doing it. Sometimes brute force is the only way to do things, but sometimes there's a better choice. One of them is greedy. So greedy would be, I make a decision, I always make the best decision I can right now, and I never reconsider my decision. Is greedy optimal? Well, sometimes. MST, greedy works with Prim's algorithm. MST, greedy works with Kruskal's. For Dijkstra's algorithm, greedy works to produce the single source shortest path. If it's undirected, we can go either direction. So Dijkstra's in an undirected graph, we can consider the direction to be either way at all. If it was a directed graph, we would have to be very careful, and it would be from the start to all others if it's directed. Okay, so greedy, we saw fractional knapsack, or MST, Prim's, Kruskal's, single source shortest path, Dijkstra's are all greedy algorithms, and they are optimal. Coin making. Coin making. Sometimes it's optimal, sometimes it's not. It depends on the denominations. We looked at divide and conquer. So divide and conquer is when we can separate something into two or more subproblems where they do not overlap. Dynamic programming is when they do overlap or reproduce the same problem over and over again. So when problems overlap is like what we saw with the tiling the board today. To solve size n, I need size n minus 1 and size n minus 2. And because I need both of those, there are overlapping problems where they are, and then to solve n minus 1, I need n minus 1 of that, which is n minus 2. So we have these repeated subproblems. Now when we do divide and conquer, it says usually recursive, not necessarily, but often. We did do divide and conquer like binary search. We wrote a recursive version for binary tree existence, and we talked about an iterative solution. So sometimes it's iterative, sometimes it's recursive. If there are two subproblems and we have to solve both subproblems, we might do it recursively, or we might use a stack or a queue to keep track of what still needs to be done. Dynamic programming, like I said, only can be done when there are overlapping subproblems, repeated subproblems, and the key to dynamic programming is we would be willing to give up some memory to save a lot of time. I'm willing to give up a chunk of memory to save a lot of time, assuming that amount of memory is reasonable. When we do Project 4, Part C, you might say, hey, wait a minute. I've got a start, like whether I started out like 0, 8, 4, 1, 2, or I started out 0, 1, 2, 4, 8, either way, the unvisited is the same. The unvisited has 3, 4, 5, 6, 7. So whoops, I've got something's wrong in there. Yeah, there's no 4 in there. Okay, so 3, 5, 6, 7. So you might say, well, hey, when I solve the MST of 3, 5, 6, 7, why don't I just save it? Well, because there's an exponential number of subproblems. So we would need exponential memory to solve all those MSTs so we don't have to recalculate them. And we don't have exponential memory. We can't really afford exponential time, but we certainly can't afford exponential memory. So we memorize, we remember those already solved subproblems so that we can look them up and reuse the answers. Backtracking is for constraint satisfaction problems. Branch and bound is for optimization problems. Now, when we're doing backtracking, we might be able to stop early. If the user is satisfied with one solution, we can stop as soon as we find their one solution. If they want all of them, then we got to keep going and provide all of them. For branch and bound, though, we can't stop early because it's almost impossible to tell if we've got an optimal solution. because the problem is so complex. We don't know what the optimum solution is. If we knew that, we wouldn't be doing branch and bound at all. So it's almost impossible to know that we can stop early because we don't know that we've found the best solution possible until we've exhausted all possibilities. Then we know what we're left as our best must have been the best possible. So there's an example in here with DP of something we've already done. So here's an example of Fibonacci. Here's a recursive version. We've already seen this. The question here is write 2 more versions. And we don't really have time. I'm going to show you the solutions, so we'll get them in the video, and you can take a look at them in more detail later. But the other question is, what family best describes that? So the solution shown below is not DP. Is it divide and conquer? No, because we don't have independent problems. That one I would call brute force. We're doing the most work possible to solve it. Okay, so I'd call that one brute force. Let's look at different solutions for this. So here's one that I used, an unordered map. This was nice because if the uint64, if I just changed the type uint64t, if I just change that, if there was a uint 128 type, I would just have to change that. I don't have to figure out what's the biggest value that fits in a uint 128t. I just let you suffer. If you try to calculate the fib of something that won't fit in a 128-bit integer, that's your fault. It's not mine. So this version just uses the static unordered map, starts out empty. If I'm trying to get n less than or equal to 1, it's a base case, return it. Otherwise, do a find. If it's not equal to the end, return found second. Otherwise, calculate the value recursively and return what you computed. So that's a top-down solution using an unordered map. Here's a bottom-up solution that doesn't need O of n memory. It just keeps a couple of variables around, so fib previous, fib current, and fib temp, and basically moves the values between them to get a running total. And just returns fib current when we're done. So you can look at those more later in the video. Okay, so answering coding questions, we already did that one. What have you learned? Okay, so you've come from the beginning of the semester with, what do you mean we don't get starter files, to the project 2, actually. Let's put project 2 in there where, oh my gosh, you gave us templated starter files and we had to do a pairing heap. To the end of the semester where now really you're implementing your own data structures, you're deciding on ways to do things, you've learned more advanced data structures to use, to optimize things in different ways, you've learned to make better choices. So hopefully you feel like you have come a long way. We know you have. You just have to realize it yourself. Where do you go from here? Well, almost all of the upper level courses. I know 485, I think, is being taught in summer semester, although it's full. There's a new course that starts this year. Actually, it's been a 398, a special topic, a few times up until now, but it got voted in as a new regular course. So that's Nicole Hamilton's Build Your Own Search Engine class. And so you'll learn what the components of a search engine are, do it. You'll learn a bit about large program decomposition. So the bad news is you'll see 381 is not in this list. Dave Kiris retired, and we did vote at a faculty meeting. It was unanimous. He wasn't allowed to retire, but he ignored us. So 381 is more or less done, unfortunately. I would say the next best thing would be 440, Nicole Hamilton's class. So she was at Microsoft when Bing was created. She wrote about 30,000 lines of the original Bing. I think she wrote the parser and result ranker. And your search engine will be considerably shorter than 30,000 lines. But it can be a real search engine. There are groups that have indexed on the order of 80 million, 85 million web pages using the search engine that they wrote in 440. Beyond that, learn on your own. Look at other libraries. If you were allowed to use them, what is out there and how do you use it? So, we're done with material for the review. I'll answer the question there in the chat window. And we'll see you for office hours. If you're not done with the project or the lab yet, we'll see you in office hours. And if not, we'll be on Piazza for the final exam.